In this video, we are going to discuss the second operation of our abstract data type of heaps. When we are discussing like min heaps, whenever we are discussing about deletion in case of min heaps, we are always going to extract the minimum element from its root, which is the root will automatically be the minimum, and we can only delete the minimum element, which is the root is going to be deleted. So how the deletion works in this case, it's quite similar to how we did it in binary trees, which is you find uh, like an easy way to do it is you replace the last element in the heap with the element that you are trying to delete, which is you'll always delete the root element. So 66 gets deleted and 66 and 8 get swapped. Next, you are going to use this operation of called heapify down. And what this operation does is it compares 66 with both its children. Now, since 66, and it finds which is the minimal child. Like if it is not, like if this value is less than both its children, it just stops because it's a valid heap already. But let's say if this value was greater, like in this case it's greater, it's going to compare with the two children and it's going to compare which is the smallest child. So in our case, here the smallest child is 11 and not 18 because 11 is smaller. So it's going to swap with the smaller child. So in this case, 11 will go up, 66 will come down. Next, it will again compare 66 with the two children, which is 39 and 29. Now the smaller child, like since 66 is still greater, it needs to go down because the smallest child would come up. So in this case, 29 is the smallest child. So 66 and 29 will be swapped. Now, in this case, like 66 doesn't have any more child. So it's also now a valid heap, which is, you can see like 11 is greater, smaller than both its children, which is 18 and 29 in our new case. 29 is again like smaller than both its children, which is 39 and 66. And the entire heap property is satisfied. So this extract minimum, which is like if we talk about like how much time does it take to extract minimum, there are two different operations. First is get minimum. So if you were to get minimum, which is like, let's say if you want to find out what is the priority, which is the element that has the highest priority. So you can get it in just O of 1 because you just need to return the root node. But let's say if we are using this operation, which is extract minimum, this will take like O of log n time because you are first deleting the last element in the array. So that's going to take like O of 1 time. Next, you're going to swap it with the first element. That will also take like O of 1 time. Finally, you're going to call the heapify down method, which compares all the elements, like the whether the heap property is violated or not, and it will continuously swap till we reach the bottom. So this swaps till we reach the leaf node is going to take like log n because we are going to take like log n time because the height of the tree is in this case it's log base 2 of n. So we'll typically make different comparisons till we reach the leaf node, and the overall time complexity of deletion in a heap is log of n. So this is the algorithm that is I just described, which is you remove the item in the root node by replacing it with the last element. Next, you keep on swapping the parent and the child. You swap the parent with the minimum of either of the children, and you keep on doing that till till you reach or you become the leaf node, which is you do not have any particular children, or the heap property is not violated. So let's see another quick example here. Like this is roughly the C++ code that you're going to implement. I'm not covering this because this is the most easiest. I feel this is the most easiest data structure to implement. and I would like you all to implement it on Stepic. We do have like space for that. So how deletion works is you first make like ARR0, which is in this case, you'll have some array that starts with 8 because you're representing this, and the last element will be 66. So you have 8, 18, 11, and followed with the last element 66. So whenever we call this delete min or extract min operation, what it's going to do is you are going to just swap these two, which is you are going to decrease the size by 1. That's what I just did. Size will now point to here. Next, ARR0 will now be 66, which is you have just deleted this element and 66 looks like this. Next, you are going to call heapify down on the index, which is 66 at the 0th index. So you are going to call heapify down. So now what this method does is it checks if the leaf, if the index is a leaf, then you just stop it, which is you have reached, like that should be your base case. Like if you are defining this recursively, it will be your base case. You can also do this iteratively. Like there are two different ways. Both of them are super easy. So I think I'm going to discuss this in the problem solving lecture next week. But right now, like you're going to check whether the index is not a leaf. Like if it's an index, you just stop. Otherwise, you find the smallest child of the node at index I. You are going to swap the node with the smallest child if, I think I have a missing if here, which is if in case it is lesser, uh, like we are going to swap this value if it is lesser than its parent. So you first find out the smallest child. Like let's say if instead of this heap, somehow this heap was 180 and 110, so then you don't do a swap because it's not violating the property. It is only violating the property if the child is smaller than its parent. So I'm missing an if clause. Like make sure you add that. You swap it with the smallest child and you heapify it down on the smallest child index now, which is you'll swap this with 66 and 11. So 11 will go up, 66 down, and now you're going to call heapify down on the index of the new index of this number 66, which is 66 might be at index 0, 1, and 2. So you are going to call like heapify down on 2. In the next video, we'll discuss something called heap sort, which is our last topic. Try to implement this. It's not hard at all, and we are going to discuss this in the problem solving lecture. Thanks.